So someone pointed out at dinner that this title is kind of like an internet advertisement. You know, it's like, number 6 will shock you. So today you're going to learn one weird trick to solve all 7 problems. I'm not going to show you all 7 right now just for time reasons, and also I want to leave a little mystery because the paper is set up sort of like a little mystery type thing, right? So it's going to ask you to think about how you would solve each problem. And shockingly, the solution has to do with the technology we've been developing for years. But so first I should point out that 3 of us actually have moved to University of Alabama, Birmingham. And that completes the slide portion of my talk. All right. So one of the co-authors, Matt Might, has a blog, and he wrote this blog post, I guess, during a slow Valentine's Day, called 99 Ways to Say I Love You in Racket. And it's to teach beginning functional programmers about lists, right? So, you know, it's just like, I love you, you know, quote, I love you, cons, quote, I, and so forth, right? So he did 99 of these things by hand. Like I said, well, not judging. Okay, so so here's a question. Say we wanted 99,000 of these, or 99 million of these, and we want the same spirit, right? We're not just going to like do Ada expansion of the list I love you. We want to show off the features of Scheme or Racket or whatever language we care about. How would you do this? What would be a fun, interesting approach to automate the generation of 99,000 programs that evaluate to I love you? Yes?
Random, execute them and see if they say I love you?
Okay, so we could just generate random programs and see if it gives us the right answer, right? Absolutely, we absolutely could, okay?
Can we use a logic engine somehow?
Okay, a logic engine? Wow, that's a good idea. Okay, let's do that. I thought I was going to have to plant my own Confederates, so this is handy. Okay. So yeah, that's a good idea. So we are going to use a logic programming engine. It's based on this language called Minicanron that we've been working on for a long time. In fact, Dan Friedman and Oleg Kislev in the audience are original creators of this language with me. But since then, many other people have helped improve it, including many people in this room. And so what we're going to do is not just use a logic engine, but we're going to use this one weird trick, which is to take a logic programming language that's designed for writing programs as relations instead of as functions. And this is a little different from Prolog because Prolog has all of these features that are called extra logical features like cut and assert and retract and so forth. If you're familiar with Prolog, that gives you control over the search and underlying features of what's going on, but those features can destroy sort of the beautiful logical aspects of Prolog, and it can make it difficult to do some of the things I'm going to show you. But you can do some of the things I'm going to show you in Prolog, but you kind of have to tweak the language quite a bit. But Minicanron is basically optimized to do these sorts of things. So the idea is we're going to write an interpreter for our language of choice. Let's say it's Scheme. And we're going to write an interpreter in Minicanron. So you can see on the left we have some operational semantics for like a little bit of Scheme. And then on the right we have a Minicanron code. Okay, so you can see the Minicanron code is not that long. For some of the versions of the interpreters I'm going to show you, we have some optimizations that make it more complicated. But the idea also is that we want to be able to kind of easily translate operational semantics into our language and so forth. Okay? So once we've done that, now we have this interpreter, we can play some fun games. So our interpreter, just like we have eval and Scheme, let's say. So let's see. If I've got eval, so I can eval, so quote, cons of 1 to 2, and that gives me the pair 1.2. Just like we have eval in Scheme, we will now have a relation called evalo. We always have an O at the end of our relation names in Minicanron. We're going to have an evalo relation, and because it's a relation, it's going to take 2 arguments instead of 1. So in a val, we have one argument, which is the expression, and it gives us back a value. Now we're not going to think about returning values. Rather, we're just going to have two arguments to evaluate. So the first argument will be the expression we care to evaluate. The second argument will be the value that we would associate with that expression. All right. So we also are going to have a sort of a run interface. So this is sort of our query language. And I can give usually a query variable like q there. And I say I want one answer. That's what the run one is. So now I can call a valo. Okay, and sort of a simple thing would be, I don't know, cons 1 onto 2, I suppose. See if that works. Yeah, that does work. All right, so what's going on here is you could see that a valo takes a second argument, q. In this case, that q is just representing the output. Okay? And we get what we expect. The only thing you notice is that we have some extra parens wrapped around it, and that's because we can return a list of answers. You really can think of it as sort of a set of answers. And there's another set of parens because we can have some side conditions that sometimes are necessary to interpret the answers when we have abstract answers. All right, so that's a valo. And we can evaluate, some sort of expression that gives us the list I love you. So I could do something like cons love to say list you. All right, that works. Now, if we want to generate an expression, a scheme expression that gives us I love you, what do we do? How do we change this? What's our one weird trick? Backquotes? Oh, backwards. What does that mean? What does backwards mean? Escape control T. Okay. Well, escape control T is yes. Okay, let's only do escape control T. I've got the new Mac, which doesn't really have an escape key, but I'll try it. Anyway. Oh. Hey! Is that what I wanted? Well, I could do run 99. I think what I want is not the cons expression. I think what I want is the list I love you. Let's try that. Okay, so now we get an answer. And it's right. Quote I love you evaluates the I love you. So well done. How about run 99 I heard? Okay, let's do that. Let's get some more. All right, here's some more. So let's pick one. What? We're just getting started. All right, how about, I don't know, let's grab this one. There's some side conditions, but, that's some lambda. Now you'll see a couple lambdas. You'll see that we have this _0. That represents, in this case, we had a side condition saying that's a symbol representing an identifier. This is basically a representation of a variadic argument in scheme. So anyway, that evaluates to I love you in scheme or racket. Okay, so that's kind of our weird trick. Our one weird trick is that we have a language which is optimized for writing things as relations, which means we can place logic variables, as basically treat them as wholes or unknowns, and we can place them in any argument or subposition of an argument and have the system fill it in. And we've written an interpreter for scheme in this language, and we've optimized it in some cases. So that's the trick, okay? So I'll give it away. That's our one weird trick, and we're going to do everything with that. All right, so that's I love you. And in fact, you can do 99,000. Yeah, actually, so I do have 99,000 here. Yeah, I've got more than that. I've got millions of them. But so here's actually a fun one. Yeah, I kind of like this one, I think. Let's run that one. Yeah. So, what's fun is once it gets complicated enough, you'll be like, no, that's not right. And then you're like, oh, actually it is right. Okay, so that's I love you. Now, once we know we can do things like that, you've got that on your brain, let's try something else. How about a challenge from John McCarthy? All right, so John McCarthy had this paper called A Micro Manual for Lisp, Not the Whole Truth. I don't know, that always gets a laugh, and I'm not sure why, but it's just like a little description of a tiny subset of scheme, or Lisp, on the left, right, these rules. And then there's a challenge. And the challenge is right here. difficult mathematical type exercise. Find a list E such that value of E is E. So value is his interpreter or his eval function, right? So do you know what the name of such a list E is? It's a quine. It's a program that evaluates to itself. All right. So can we use our one weird trick to find a quine? Okay, all right. You're going to... Fine. I should have known. Yes. We can do that. We could do it both ways, actually. Well, okay, let's do it. Since you insist on that, let's try it that way first. So let's load. We've got various versions of the interpreter that have different language features. So let's try doing a run one E, and we have evalo. So what should our query be? EE, right? So we want the expression and the value to be the same. All right? Okay. So in this particular interpreter, the first answer is an abstract integer or a number. Okay? So any number is indeed a quine in Scheme. So if I can type in 5, that evaluates to 5. Great. All right. How about two of these answers? Let's do run 2. All right, I get hash t, which is true. All right, okay, this isn't looking that good. Hash f is false. All right, so let's, oh, what is that one? Oh, that one looks more interesting. Yeah, that one's a quine. Okay. Okay, so what if we wanted twines? What if we wanted twines, which are two programs, P and Q, such that P evaluates to Q and Q evaluates to P, and they differ? How do we do that? Escape control. All right. Well, first of all, the real answer is I'm going to change interpreters. So we don't sit here for a while. It'll come back, but I only have 18 minutes total. All right, so let's do it for real here. So let's do our run one. So I told you there's P and Q. So, we can have more than one query variable. How about we have P and Q? And so now what am I going to do? What would I write? And the language is so sophisticated, there is no, well, there kind of is an and, but we don't have to write it as implicit, just like begin is implicit in Scheme. So we don't even have to write that. We just write an evalo. So what should I write? PQ, okay. What else should I write? Evalo QP. Anything else? Yeah, I need to make sure they're not the same, right? Because every quine is trivially twine. Okay, so I need P and Q to be different. All right, so let's see what I got. All right, so I've got two values. So let me just look at the first one. Notice that one has a quote. I get back an expression without a quote. I'll evaluate the expression without a quote. I get back a quote. All right, so those are twines. And you could do thrines and all sorts of other things, right? So you're getting the idea. This is the one weird trick. All right, let's see what else we can do. Okay. Yeah. So let's do, how about we do a look at a proof checker. So this is a proof checker. I'll show you the simple one. This is a proof checker that Matt Might wrote in Racket for some reason. I don't know, he was writing a blog post or for a class or something. So it's just a little proof checker for propositional logic, and it has modus ponens and assumptions. That's it. Okay? And because this is a proof checker, actually, I'll show you. Here's the version in Racket. It's the same code. So here's the proof checker version. And basically, you have to supply the entire proof. Here we're proving from an assumption that we assume A, and we assume A implies B, and B implies C. We're trying to prove C. So we have to give the entire proof. And we get back hash t saying that that's valid. OK, So now what we're going to do is we are going to take the code literally without changing it, stick it into our evaluate relational interpreter, and then we're going to do what? Replace the proof with Q, and we probably want to put a hash T here as the output. What happens if we put a hash F? We'll only generate invalid proofs, which we can do if we want, but let's say we want to. Yeah. Okay, so let's try that. Run it. And that's the proof we get back. And that looks remarkably close to the proof we had to write by hand. So now our proof checker is a theorem prover. Right? So Matt wrote that proof checker before we had this technology working. So that was kind of fun to be able to go back. All right. So I'm getting low on time, so let me just show you, I think, one more. And you can look at the paper for other fun stuff. Oh yeah, I just got to show you this one real quick. I'm not even going to talk about this one, but I wouldn't be a schemer or a racketer if I didn't also write a metacircular interpreter in the interpreter, right? And this gives you, by the way, the ability to reason about higher order environments and procedures, closures, that sort of thing in Minikanren, which is only a first order language, only has first order syntactic unification. So that's a fun example as well. All right, so the last example I'm going to show you is, which is something in the paper, but I'm going to show you a slightly different interface. This is a tool called Barliman that we've been working on, which is sort of a front end on what I'm showing you. And basically, what I'm going to do is I've got a partial definition of a function. So comma A, comma B, comma C, those are variables that represent wholes, unknown expressions. And now I'm going to write some examples down. So let's say we define append. Append the empty list to the empty list. Should be the empty list. Barliman thinks, it's like, hey, I think you're defining a function called append, and it takes one variadic argument and returns the empty list. Okay, so let's see if we can do better. So let's say append A to B, and that's going to give us AB. It's going to think, oh, it's going to do a little better, but it's still specialized. So we invent the eigenvariable, and I'll add that. Okay, and this should help it keep from specializing. Great, but we haven't gotten the recursion yet, so I'll do one more.
So you can hide the function definition.
Well, we'll see.
Why do you have quotes instead of quasi?
Because it's a little hack to make the quasi quotes work, or to make the gensims work. Okay, that's actually the correct definition. It's a little hard to read. So this is actually an IDE. It's not a very good IDE, but it's an IDE. So I will add some variable names here. Let's say L and S. And now you can read it, and that's the correct definition of append. And one more thing I'll show you real quick, and then go on the questions. I can add, say, two more examples here. And if I'm writing the definition of append, because I can't synthesize it because it's too long, then I might do something like, say, if null of L, return S, otherwise return something I don't know, I'm filling it in. This is correct, and I can synthesize it faster. But maybe I make a mistake and I type in L, and it refutes, even though I've got a hole in my program that could be arbitrarily large. So the cool thing to me is that we weren't building a program synthesis tool. We just sort of get this for free, although we have to do some optimizations, some pretty significant optimizations to make this, this technology work, and we're still trying to improve that. Questions?
Okay, thanks, Will.